In this video, we're going to talk about continuity. So first off is a little bit of an introduction. So we have the limit as x approaches -2 from the left side. So as we approach -2 from the left side, it is approaching the y value of 2. Then we have the limit as x approaches -2 from the right side. As we approach from the right side, it is approaching -1. So that means that the overall limit as x approaches -2 does not exist. And then when we evaluate f of -2, we're looking for where it's defined, and that would be right here at that closed circle that has a y value of 2. So is f of x continuous at x equals -2? No, it's not. It has what we call a jump discontinuity. Okay, so this is a jump discontinuity. And I'm going to abbreviate discontinuity. Okay, moving on to the next one, the limit as x approaches 0 from the left side. So the limit as x approaches 0 from the left side is 1. The limit as x approaches 0 from the right side, that would also be 1. The limit as x approaches 0 overall, since the left side is equal to 1, the right side equals 1, that means the overall limit is equal to 1. And then evaluating f of 0, that would also be 1. And so is f of x continuous at x equals 0? The answer is yes. Lastly, the limit as x approaches 3 from the left side. As we approach 3 from the left side, it is approaching 0. As we approach 3 from the right side, the graph is approaching 0. So therefore, the overall limit as x approaches 3 is approaching 0. And f of 3 is where f of 3 is defined. That is down here at -1. So is f of x continuous at x equals 3? The answer is no. This is what we know as a removable discontinuity, because a part has been removed from the graph. So we have 3 different types of discontinuity. We have a jump discontinuity, which is happening at x equals -2. We have a removable discontinuity, which is happening at x equals 3. And the last one we have is an infinite discontinuity. And that is what looks like it's going towards either positive infinity or negative infinity. So if it's going towards positive infinity, it would look like this. So it is a discontinuity, and the limit does not exist here, but the limit could also be approaching infinity. Okay, we also have if it would be going towards negative infinity. And then the last one would be when one side is going up towards positive infinity and the other side is going down towards negative infinity. Okay, so that's the 3 different ways that infinite discontinuity could look like. Again, x equals -2 is a jump discontinuity, and at x equals 3, you have a removable discontinuity. Now, based on what we saw in this introduction, what do we think we could come up with to say if a function is continuous at a specific point or a specific x value? So hopefully you're thinking that the limit has to exist and evaluating at a function has to exist. Therefore, also the limit has to equal the value for our function to be continuous. Okay, so we have an example where the limit does not exist and our function was not continuous at that point. We have an example where the limit does exist and we can evaluate it at that point, but because the limit and that point are not equal, then it's not continuous. But when we look at f of x being continuous at x equals 0, notice that the limit is equal to when we evaluate. So what we can say as our rule is that our function is going to be continuous at x equals c, where c is any number, if I keep spelling words wrong. There we go. If the limit as x approaches c from the left side of f of x is equal to the limit as x approaches c from the right side of f of x is equal to f of c. Okay, so those three things have to be true in order for our function to be continuous, and we're going to be using this throughout the entire lesson. So here are some notes. This right here is the important part. That is the exact same thing we just said. F of c has to be defined. F of the limit as x approaches c of f of x has to exist, and the limit as x approaches c of f of x has to equal f of c, which is the same thing that we just wrote. So again, I'm going to write it again. Continuous at x equals c, and this is going to be the work we show every single time. So these are the steps that we follow. We're not going to change our steps. So the limit as x approaches c from the left side of f of x has to equal the limit as x approaches c from the right side of f of x. That is step 2. That's showing that our limit does exist. And then it has to be equal to f of c. And f of c existing or being defined would allow that to happen. Okay, so we're going to go through several examples in this video just to get some practice. And again, this right here is going to be written every single time. So example 1, using h below, for what values of x is h not continuous, and justify. So if we're looking at this right here, we have some linear functions, we have a polynomial function. Polynomial functions are continuous on its entire interval. Okay, the really only time you have to focus on when they're not continuous is when you're dealing with like a rational function, the natural log, or even an exponential function. Okay, but polynomial functions include linear functions, quadratic, polynomials, and so cubic. They're all continuous. So we have to see if this is continuous. Well, the only issue we would have with it not being continuous would be right here at -2. So what we're going to do is we're going to determine if this function is continuous at -2. So our steps, we write continuous at x equals -2. And so we are going to evaluate the limit as x approaches -2 from the left side of h of x, make sure you use the correct name, is equal to the limit as x approaches c from the right side of h of x, which is going to be equal to h of -2. So if I'm approaching h of x from the left side of -2, I will be using this top equation. And so when I plug in -2 there, I get -2 times -2, which is 4. And 4 minus 5 is a -1. We're trying to see, is that equal to when we approach the limit from the right side? So when we are approaching from the right side, we are going to use this equation right here. So when we plug in -2, we get -8 minus 12 or plus 12 plus 3. So that would be 4 plus 3, which is 7. And that part right there shows us that these are not equal. But let's go ahead and check h of -2. So when we plug in -2, that is where we'll use the middle equation, because the middle equation says that's when x is equal to -2. And so we would get 3. And so that is not equal. So what this tells us is that h of x is actually not continuous at x equals -2, and we need to summarize that. So h of x is not continuous at x equals -2 because And we can say just because the limit doesn't exist, because the limit doesn't exist, because the left side does not equal the right side. So because the limit as x approaches -2 of h of x does not exist. And that would be our answer that we're looking for. Okay, so looking at the next one, for what values of the constant c is the function g continuous over the reals? So same exact concept. So we're going to do the same thing. The only place where it could not be continuous is at x equals 3. And so we do the same setup. We're going to see that it's continuous at x equals 3. And so we're going to look at the limit as x approaches 3 from the left side of g of x. The limit as x approaches 3 from the right side of g of x. And we're going to evaluate g of 3. So the limit as x approaches 3 from the right side, or sorry, the left side of g of x is that top equation. So I'm going to plug in 3 for x. When I plug in 3 for x, I get 3c plus 1. Then I plug in 3 in the second equation. So that would be 3 squared, which is 9. So we get 9c minus 1. Again, for the first equation, or for the left side, we use the first equation. And for the right side, we are using the second equation. And again, I'm plugging in 3 for the letter x, and we're trying to solve for c. For g of 3, we're going to use that top equation again. So we would get 3c plus 1. And we're using that top equation because it has the or equal to. So we want to solve for the value of c. Well, we have an equation right here. This is just a repeat, so you don't have to worry about it being set equal to 3 things. You just worry about that part right there. And so I'm going to take 3c plus 1 equal to 9c minus 1, and we're going to solve for c. So I'm going to subtract 3 from both sides and get 6c. I'm going to add 1 to both sides, and I get 2. And then I'm going to divide both sides by 6. 2 over 6 simplifies to a 1/3. And so c is equal to a 1/3. Okay, that value of c would make our function continuous over all of the reals. Okay, so number 3, same concept, just a different variable. So we want to find a so that the function below is continuous everywhere. So the only point that it cannot be continuous or potentially not be continuous is -4. So we're going to do continuous at x equals -4. And again, the same setup every single time. So the limit as x approaches -4 of f of x, and it has to be from the left side, is equal to the limit as x approaches -4 from the right side of f of x, has to be equal to f of -4. So now we're going to plug in -4. So from the left side, we're going to use that top equation. And -4 plus 11 is 7. From the right side, we're using that bottom equation. So I am going to get 16a minus 11, because 4 times -4 is -16. -16 plus 5 is a -11. And then when I evaluate f of -4, that would also be 16a minus 11. So once again, we want to solve for a. I have an equation right here that we just need to focus on. So 7 equals 16a minus 11. I'm going to add 11 to both sides and get 18 equals 16a. I divide both sides by 16 and I reduce it to get 9 over 8. So A is equal to 9 over 8. Okay. So, number 4, if you want to pause the video and try it yourself, you're more than welcome to do so, but I'm going to keep on going. So, we want to find C so that the function below is continuous everywhere. So, same concept. The only place that we need to check would be at 2. So, we are going to check that it's continuous at x equals 2. So, we're going to take the limit as x approaches 2 from the left side of g of x equal to the limit as x approaches 2 from the right side of g of x equals g of 2. So for the top equation, that will be from the left side. So when I plug in 2, I get 2 squared, which is 4c. Then I get 2 times 3, which is 6, minus 1, which is 5. Then from the right side would be the bottom equation. So that would be 2 squared is 4. 4 plus 4 is 8. And then plus 2c. And then g of 2 would be where it's equal to. So that would also be 2c plus 8. So just like before, we're going to solve this equation right here for what c equals. So I have 4c plus 5 equal to 2c plus 8. I'm going to subtract 2 from both sides to get 2c, subtract 5 from both sides to get 3. C is equal to a 3 halves. Okay. Number 5, is f continuous? Justify. So this one, we're just justifying if this is continuous or not. So here we go, same setup. We're going to check to see if it's continuous. The only value that we need to check to see if it's continuous is at x equals 0 because these numbers are 0. If there are more than one number, then you would need to check multiple numbers. Okay, but this one only has one number. So the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x is equal to f of 0. So from the left side is the top equation. So when I plug in 0, I get a negative 1. When I want to look at it from the right side, that is the middle equation. So when I plug in 0, I get negative 1. And evaluating f of 0 would actually be that last equation, which equals 2. So the limit does exist because the left side and the right side are equal, but it does not equal when we evaluate at f of 0. So this is not a continuous function. So you have to summarize that as your justification. So f of x is not continuous at x equals 0 because the limit as x approaches 0 of f of x, so the overall limit, does not equal f of 0. And that would be your final answer. So again, the justification is your answer like that. So this is you stating you know that the limit exists, but the limit does not equal f of 0, so therefore it is not a continuous function. Okay. Number 6, this is our last one. So if you want to pause the video to try, you can. A and B are 2 separate questions in itself. So let f be the function defined as follows. If a equals 2 and b equals 3, is f continuous for all x? Justify your answer. So again, we're going to check to see if it's continuous at 1. So continuous at x equals 1. That would be the limit as x approaches 1 from the left side of f of x equal to the limit as x approaches 1 from the right side of f of x equaling f of 1. So when I plug in 1 into the top equation, because that's from the left, we get 2. Now, in that bottom equation, we do have to be careful because a is equal to 2, b is equal to 3. So when I plug in 1, I would get 2 times 1 squared plus 3 times 1. That is just 2 plus 3, which is 5. If we evaluate f of 1, that would also be 5. So this is not equal right there. So because that's not equal, the limit does not exist, which means our function is not continuous. So f of x is not continuous at x equals 1 because the limit as x approaches 1 of f of x does not exist. And that would be your answer. Okay. Next one. Describe all values of a and b for which f is a continuous function. So this is completely different than a. So we're trying to now find a and b. So we're still going to check that it's continuous at 1, because that's the only place that it could be discontinuous. So we have the limit as x approaches 1 from the left side of f of x. Again, the setup is always the same. The limit as x approaches 1 from the right side of f of x is equal to f of 1. So when I go from the left side, I'm still going to get 2. But this time when we come from the right side, we're plugging in 1 for x, and that leaves us with a plus b. And when we evaluate, we get a plus b. So it wants to describe all values of a and b for which f of x is continuous, and that would be 2 is equal to a plus b. That would describe all values. Whatever a is, it needs to be able to be added to get 2, or b and a need to be added to get 2. So depending on what a is, that's going to depend what b is, so on and so forth. Okay. Now, in these examples, we did not have any that were necessarily continuous. So when something is continuous, okay, a sample statement would be f of x is continuous at x equals, I'm just going to use c, because the limit as x approaches c of f of x is equal to f of c. Okay, so that would be an example sentence if you had something that was continuous, because you do have to work on writing your sentences. So you've seen it when the limit doesn't exist. You've seen it when the limit doesn't equal when you evaluate the function. So you've seen the different variations of how to write the sentence whenever the limit doesn't exist. And I wanted to make sure that you saw when the limit does exist, what that sentence would look like. So hopefully this helps you with this video. If you need to watch it again, you can. Go ahead and do the check for understanding, and then check the answers that are posted in Canvas. That way you can see if you did them right, and always come with questions if you ever have them.